Yes, the idea is to present today our approach to photonic quantum processor and just using a single photon. The idea is to be able to enable the edge computation, not starting from the big infrastructure at the cloud side, but to the edge where data are produced. And so to be able to design small processor that can be in some way integrated inside embedded computers or edge computers. So we use a single photon to design the deterministic qubit, two qubit gates. The idea is to use the orbital angular momentum. In this way, we are able to represent many qubits inside the same photon, and this will remove the need for ancilla photon during logic execution. And not only that, we have also another interesting way to remove the error or the error correction that is based on a fault detection and without any measurement during the execution of the operation, but just at the end. This is, of course, compatible with silicon photonics, and what we want, and this was one of the reasons to design this, is has to be room temperature, no cryogenics involved in all the processing. And just two words about on the orbital angular momentum. It is a property of photons that is not used in telecom, and this in some way the result of the total angular momentum, that is spin momentum and orbital angular momentum. And in this way you have many states that you can use more than just the spin state, and you can see that in this way we can insert inside one photon at least two qubit using just the level one of the orbital angular momentum. This is the idea to build this deterministic two qubit gate that are essential for a quantum circuit. So with just one photon, we can design all the gates that are required to achieve an universal quantum computer, and without a need for ancilla photon during gate execution or no post-selection, and all linear optics. With this part, then we have had the fault detection that is using the symmetry breaking of the OM. And also in this way, we do not need to make any sort of correction with additional qubit. It is because these are flying qubit, we just repeat. We repeat, we measure and repeat, and in this way we can have the equivalence of the logic qubit with a physical qubit. So we move the problem on time. Instead to move the problem on having more qubits, we just move the problem from same qubit, more repetition. And of course, this is just an accelerator. So the idea is to combine this kind of accelerator with traditional computer. And in our roadmap, we have three form factor, a single chip, a desktop, and a down card, according to the use and according to our timeline in the miniaturization. So with this kind of things, we can move for instance, this is an example of an AI application at the edge, in which we have an hybrid quantum gun, and this is our last processor that is a 4-qubit processor. And with this, we can have a quantum generator and a classic discriminator. and we can dramatically improve the efficiency of the GAN algorithm using this combination of classic and quantum. And the idea is to be able to move all these quantum and classic things where data are produced. So inside sensor, close to the what it is the edge of the network, and to have a much more intelligent edge. And just to show in terms of dimension, how big is this stuff now? The processor is, yes, as you can imagine, a small silicon device. Then it is packaged in a big package now. And then, well, it is just the detection stage and the generation and the single photo generation stage. And of course, now we are working to miniaturize the section 4 and 5. Now we are on the 4, and for the end of the year, we will have all all the generation inside the chip. And then next year, we will move all the detection system inside the silicon. Just to recap, it's with this approach, we consider this a new step in quantum photonics. Of course, photons are great stuff, low the coherence, they can work at room temperature. The point is how you can create a deterministic gate with this. We have solved the problem of the deterministic gate with photons. And by the way, we are opening a space of infinite state space using the orbital angular momentum. At this stage, we just have 2 qubits, and we are moving at 3 per photon soon. And all this, there is a very well theoretical foundation. That is a paper from our CTO on how to use this property of light as a bosonic Majorana field, and with this, where this approach is unique, it's because of this twisted light that has many qubits in the same photon. Because in this way we can use the natural entanglement of the state inside the photon. So, and that's give us the deterministic gate logic. And then we leverage this topological qubit in order to have a topological error detection. And this means that it is much easier to build this error detection and also handling the correction. And that's my speech is concluded. It's concluded.
Okay, thank you very much, Roberto. Great presentation. Very interesting developments you're doing. So let me, as always, ask you, where is the room for collaboration with our community?
Oh, a lot of room. We are looking for the point of managing orbital angular momentum require factories, silicon foundry that has a very deep control of the geometry. The orbital angular momentum is not easy to manage. The geometrical things are very critical, and also the thickness is a little bit different from the thickness of the telecom sector. They try to avoid the multimode. We are in a multimode waveguide, and multimode waveguide are thicker than the monomode waveguide. So we hope that we are now producing here in Europe these things. I think that Europe has to invest more on the silicon foundry. We want to remain fabless, so we look for foundry first, and second, we look also for laser producer that has very small and compact laser. We just designed the source in terms of from a laser to a single photon. The circuit that is designed by us, but not the laser. So very small and compact laser. And then the detection section that has to be a room temperature. So the detection section has to be more close to what is a camera, a CMOS camera. So a single photon CMOS detector. And So that is another stage that it's for the next year, as I have said. So foundry, detectors, and laser. We take care
Good.
of the source and of the circuit.